Our final session is Automating Test and Evaluation, in which you will learn about research efforts in scaling test and evaluation and assuring non-deterministic software-based systems. You will also learn about the collaboration involved in research to create tools for automated code repair.
All right, I'm going to talk with you all about scaling automated test and evaluation. I'm going to, first of all, talk about what we're trying to do to scale testing and evaluation to make it less expensive, take less time, use less memory and space. And then I'll go into detail about a few research projects. One is mine. And I'll talk about some tools that we've developed that are available to help you all in your testing and evaluation. I'm Lori Flynn. The problem that we're talking about is that complex software is business and mission critical. The software is developing quickly to be more complex, and the impact of that over time is that well, actually, is shown in, with the example on this slide with the evolution of avionics size and function from the F4A in 1960 to the F-35 in 2000. So the F4A is shown in the black and white photo and the F-35 in the color. So over time, the significant lines of code have increased from 1,000 to 9 million. And the percentage of the airplane function that's done by software has increased from 8 to 80%. And that kind of complexity is typical over time, and you can see that the impact to life and mission is likewise increasing. Catching software faults early saves money. Faults account for 30 to 50% of total software project costs, according to these 5 cited resources and others. The gray arrow at the top of this slide represents the software development lifecycle with various phases of the lifecycle. The important thing to note is that on the left side, early in the lifecycle, very few of the faults are caught there, and yet the cost per fault detection and removal is very low compared to late in the software development lifecycle, where at the latest stage in operations, where 20% of the faults are detected, the cost per fault removal is 300 to 1,000 times the cost of detection and removal in the early phases. So testing is important for catching faults, and we want to move to the left to the earlier software development phases to make catching them more scalable, cost less, and happen faster. So scaling this, the topics I'll talk about address all 4 topics we've been talking about throughout the research review that are the enduring software challenges, affordability, capability, trustworthiness, and timeliness. And they address state-of-the-art and state-of-the-practice challenges. So testing, various testing methods are listed here. 3 are now highlighted with the red boxes. Those apply to research projects and tools that I'll talk about today. Architecture design analysis has the strength that it can help in early identification of costly defects, but it has the issue that sometimes it can be conceptual and early and miss finding issues that are developed later during later software development phases. Static analysis compared to dynamic analysis, both static analysis and dynamic analysis analyze code Static analysis analyzes code without executing it, and compared to dynamic analysis, generally involves more thorough coverage, but its weakness, or some of its weaknesses include that it can have high false positive rates, or conversely, it can have high false negative rates, meaning that it doesn't find enough of the flaws. Actually, I'm not going to be talking about dynamic analysis. The next one down should be highlighted. I'll be talking about formal methods which prove software attributes. The weaknesses associated with that are that it requires significant time and space, resources, plus model validation is challenging, and it requires significant manual effort. So our work here at the SEI tries to address those weaknesses related to these methods and come up with new techniques and tools that help to perform those types of tests. Purposes for testing can include unit testing to test small bits of functionality, integration system testing to test how parts of a system interact and make sure they interact correctly, regression testing tests to look for flaws that have been introduced during development, often reusing unit tests, and acceptance testing checks to see if code is ready for delivery and that it meets requirements. The evolution of testing in terms of scalability, in terms of ease of doing the testing and lower cost and fast and speed starts with manual inspection. We humans are expensive and we can be slow. Then tool-supported integrated testing, for instance, testing within an IDE as part of continuous integration, automated testing and automated repair. Now, we can't do all types of testing in an automated way. And even tests that we can do in an automated way cannot necessarily be repaired automatically. But as possible, we would like to move towards the more scalable methods of testing and then follow them with automated repairs. This slide is one that I think Hassan Yassar showed yesterday during his DevOps talk. The purpose of this testing is ideally to fit within this secure DevOps model, where DevSecOps is the model that integrates the software development and operational processes considering security activities, starting with requirements and going through design, coding, testing, and delivering, and doing testing as scalably as possible throughout the system. And then our final goal is code that not only just passes the test, but the purpose of the test is to have more secure code that does what it is supposed to do functionally. So scaling testing, at SEI, we're researching how to make testing less expensive, more precise, and automatable. And we also research scalable automated repairs following testing. The first research project I'll talk about is predicting security flaws through architectural flaws. It addresses two of the enduring software challenges we've talked about, affordability and trustworthiness, and it addresses state of the practice. The problem it addresses is software security defects, increasing risk exposure, and costing money. Existing analysis methods have limitations. Some security flaws are introduced by code structure and module relationships, which are often not found or fixed locally. We're talking about architectural issues. An example that those researchers found was in in a software project was that 19 configuration files were required for cross-platform support to define a library's usage. However, then a vulnerability was discovered in this library. So in reaction, configuration files were changed to mitigate that vulnerability by restricting use of the library. But it turned out some of the configuration files aren't changed correctly, and the vulnerability persists. So architectural issues can lead to security flaws. That's one example. This is an example that involves a lot more data. This slide shows the impact of issues involving more than 10 files in the Chromium codebase. Chromium, of course, is the open source software that is the basis of the Chrome browser, a web browser used by over 1 billion with a B people worldwide. So on the right, the pie chart shows the percentage of security issues that involve more than 10 files. It's very small, only 7%. However, on the left, you see that about 50% of the total effort measured by changes in lines of code to fix security issues in Chromium came from fixing that 7% of security issues that involve more than 10 files. So that architectural flaw or architectural issue affects security and effort, meaning cost, in a really large way. So that was the inspiration for these researchers' work. This slide shows the approach today to identifying and refactoring code, identifying architectural issues and refactoring code in response to finding those issues. So on the left, you see a few things are fed into tools. Source code, a revision history, meaning log files like from Git repositories, and an issue list. Think Jira issues. Those are fed into tools such as, in this example, the Understand Static Analysis tool, that's a commercial tool, and Titan, which is an SEI developed tool. That together they output this design structure matrix, which there's an image of below. The overall idea is that the tools output a set of identified architectural flaws and anti-patterns. And using that information as input, analysis, whether automated or manual or some combination, analysis is done, and that results in patterns and guidance to guidance about which refactoring should be done and which priority it should be done in. The researchers' approach, or their vision and their approach to enhance the previous way of doing things is shown in this slide. One new thing you can see is on the bottom, or in the middle, actually, there's a new item, issue list security flaws. It's actually an old item. You see in the list of those 3 inputs above, there's an issue list. This is just a filtered issue list, so security flaws are filtered out. Those security flaws are analyzed along with that initial tool output, the architectural flaws and anti-patterns. So they're analyzed for correlations between architecture and security flaws to develop predictive models for security fixes via architectural refactoring. And in the end, at the top right, you can see that the original output is still there, the patterns and guidance, but it's enhanced by 2 new things, security likelihood and return on investment for fixes. So that additional information is envisioned to help the people who make decisions, people or systems that make decisions about which architectural refactoring should be done next and what makes sense to do financially. So their overall vision is, in their end goal is that this type of system would be used in a build pipeline as part of the software development lifecycle and could potentially be automated. It could potentially be automated. So their current progress and results are shown here. They've analyzed 3 open source code bases, Chromium, OpenSSL, and Mozilla. They've analyzed 6,000 Chromium issues after commits, and they split the set of issues that they analyzed exactly 50-50, with 50% being security, 50% non-security, to try to see what the differences were and have between security and non-security issues. They also analyzed 1,600 Chromium issues both before and after commits. Currently, the researchers are analyzing the entire Chromium project over the entire per file history. This just means that they're analyzing using the repository log files. And finally, they're currently analyzing Chromium issue chains, meaning like the JIRA issues, for common files. When files for particular issues were committed to the repository together, those are common files. They've developed some software tools, scripts for data extraction from the code repository and issue logs, and for filtering, categorizing, and analyzing data. And they've made some findings, but they're still analyzing some initial findings, but they're still analyzing to determine what the statistical significance of those findings are. In past work, architectural flaws have been, in past work by the same researchers, architectural flaws have been strongly correlated with security flaws at a project-wide level. And right now they are working to define architectural flaws at varying levels of precision to make that correlative analysis that they're working on. Okay, the next project is one that I'm the PI for, rapid construction of accurate automatic alert handling system. It addresses all 4 of the enduring challenges we've been talking about: affordability, capability, trustworthiness, and timeliness, and addresses state-of-the-art and state of the practice. The problem that we're addressing in this research is that there are too many static analysis alerts. Every organization that I've talked with suffers from that, every organization that does static analysis. The solution we're doing research on is automation of handling those alerts as much as possible and as accurately as possible. So for static analysis, the situation, or the static analysis flow of activity starts from the left of the top of this diagram, where code bases are analyzed by one or more static analysis tools, each of which outputs a set of alerts or warnings. And today, following the arrows at the top, those need to be analyzed by a person, by an engineer who marks them with a determination. For instance, a true positive or a false positive. Now, the situation today, so with this manual examination, with this manual examination, some alerts are examined and marked true, some are marked false. Those are shown on this chart in the top right. That's a typical chart where the number of alerts that have been manually examined are often small, and the number of alerts that have not been examined manually are often large. And the problem is the ones that haven't been examined might be severe faults, or severe flaws. For instance, there could be a vulnerability that could be remotely exploited with no initial privileges, but that wasn't found by manual examination. So our project goal is shown in the bottom. We're working to develop an architecture that classifies alerts using automatically labeled and organizationally audited data, or manually audited alerts, that accurately classifies most of the alerts as expected true positive, expected false positive, and the rest as indeterminate. So our goal is shown with those green bars on the bottom right that are very big, expected true and false positive alerts. And just a small number, circle, or with a yellow rectangle, that need to be examined manually. So hopefully that will be a number that the organization can afford to manually examine. And we're also doing research about prioritizing those alerts using the organization's priority. This research builds the research in FY18 that I've done, builds on FY16 and FY17 related research. So in FY16, the issue that we addressed was classifier accuracy. There was one small, novel approach that I added. It was just using multiple static analysis tools as features to advanced classifiers, and we're happy with the results. It turned out that the multiple features increased accuracy. There's a lot of previous research that showed that for single static analysis tools, a lot of the features that we used and classifiers worked pretty well. So we found a new feature that helped. But so in FY17, the research project addressed an issue that we found in the FY16 work. It's that we had too little labeled data for accurate classifiers for some conditions, where a condition is some type of code flaw, a CWE or a certain coding rule or a MISRA rule. So the novel approach that year was to use test suites like Juliet or Stone Soup to automate production of labeled, meaning true or false, alert archives for many conditions. And the result was high accuracy for more conditions than before. So in FY18 now, the issue that we're addressing, or that we addressed in FY18, is that there's little use of automated alert classifier technology in most organizations, especially in DoD organizations. We've seen that. It requires a lot of money to set up such a system. There isn't an easy to adopt open source system. It requires a lot of data if you want to be able to have accurate classifiers for many conditions. And it requires experts, stats experts, software engineering experts, et cetera. So it's expensive. So there's little adoption of it yet, and we want to help. So our approach this year is developing an extensible architecture with building on that novel test suite data method from last year. And the results so far is an extensible architecture API definition, software to instantiate the architecture, and adaptive heuristic research, which is continuing into FY19. So some of the artifacts that we've developed include code, an API definition in Swagger, and code development from that instantiates that. The servers that are auto-generated from Swagger from the API definition. Scale version 2, a static analysis alert auditing tool, which has some new features added for prioritization and classification. We released it to collaborators late last year and early this year, and we released it to a version of that with a couple tweaks for bug fixes and performance enhancements. We released that publicly on GitHub in August this year. This is the first ever SEI release of Scale to the public. Scale version 3, we've released to collaborators only so far. Eventually, after we publish some papers, our intention is to release Scale version 3 or 4, whatever version is ready by then, to the public. And in terms of code development, we've also developed and tested classifiers and developed code that enables speculative mappings to CWEs for tools that don't output warnings in terms of CWEs. Non-code publications and papers include the architecture API definition and new Scale features. This month, we're going to be publishing a tech report that has the API definition, and our hope is that not only our collaborators, but others will implement the API calls or use the new Scale with the intention that it help them to start to use classifiers and advanced prioritization with minimal development required on your part, and hopefully you can take advantage of what we've built. Classifier development, research methods and results, publications and papers that are listed here, and precise mappings that I'll talk about in detail in some future slides, but right now, just to summarize, they're on the CertC standard public wiki, including the CERT manifest for the Juliet test suite, which was developed by others to test for CWEs, but we've found a way to use it to test for cert rule coverage with tens of thousands of tests that can be used for that. Also, we've published the per rule precise CWE mapping that I'll talk about more later. The initial CWE results were significant in that we developed a lot of new data for creating classifiers. With 8 static analysis tools run on Juliet, we had about 38,000 automatically labeled true and false results, which saved a lot of time, and even if somebody had analyzed, if an organization had analyzed manually analyzed that many alerts, the odds that they would have covered as many CWEs as our data covered is in that many, with as little, sorry, even if they took 117 seconds per alert audit using some previous research results from a large Google study, it would have taken a minimum of 1230 hours, but the odds that they would have hit all the CWEs that we hit and all the different sub-conditions of CWEs that the Juliet test suite tests for is just not realistic. So realistically, it would take an enormous amount of time to generate that much data, and with our infrastructure, we can easily generate a lot more data with other static analysis tools added. This slide shows, let's see, on the bottom, the chart simply has definitions like of accuracy and precision. The chart at the top is what you should focus on. That has our initial holdout data, our initial results of running Juliet test suite classifiers on holdout data. The rows show results for 4 different types of classifiers: random forests, late GBM, XGBoost, and lasso logistic regression. The main takeaway is they had really high accuracy and precision, which sounds great, but I'm going to talk about adaptive heuristics in a little bit, which we're working on because that holdout data is not the same as natural program data. Okay, the architecture that we developed is shown here. The light gray boxes show the 4 servers and their API calls for all communication between those servers. Starting at the top right, the statistics module is where the classifier, where we store, create, and run classifier algorithms. At the bottom right is the data hub module that stores data. At the bottom left is the prioritization module, which stores and evaluates advanced prioritization modules, or advanced prioritization formulas. And the UI module at the top left is where the user interface is. So we envision that organizations who have developed their own static analysis tools or aggregator tools for auditing alerts can simply instantiate the API calls required for the API for the UI module, and then they get the benefit of the classification and prioritization with the software that will deliver as part of this architecture. So we've developed Scale. So Scale can be used as the UI module, but any other organization that wants to quickly start to use classifiers and advanced prioritization are welcomed to try out using our system and simply by developing those instantiating the API calls. So for instance, in systems like DHS Swamp or Army CertX SWAT or any other alert aggregator tools or single static analysis tools could do such a thing. The architectural development used the representational state transfer REST style using a set of constraints and properties based on HTTP. And we use Swagger because it is very widely used and it's free. So we want to make it as easy as possible for lots of organizations to use our architecture. And in fact, it turned out some of our DoD collaborators are using Swagger for their alert aggregator tools. Continuing work in FY19 on this involves using test suite data, involves research on adaptive heuristics, looking at how classifiers should incorporate new data, using test suite versus non-test suite data, where either new data can come in at any time, but what's the best way to combine them for accurate classifiers, while also weighting recent data, which is a common thing with adaptive heuristics. We're also going to be using semantic features for cross-project prediction, which has been used successfully recently. There have been publications about using that for increasing accuracy of cross-project prediction, different projects within the same organization or across organizations. And our test suites they're a different type of a project. So a test suite versus non-test suite has features that are similar. Also in FY19, we're hoping to get as many possible collaborators to implement our API so I would welcome any of you all contacting me about doing that. And more collaborator audit archive data sharing. If you use Scale, we provide a data sanitizer for that, and if you use a different system, we could help you to sanitize your data, so you could feel comfortable sharing your audit archive data without sharing sensitive data. The next project I'll talk about is can deep learning predict security defects in synthetic code? This project addresses capability and trustworthiness and state-of-the-art enduring software challenges. The problem this research project addressed is that predicting security defects in source code is of significant national security interest, but existing static analysis tools have unacceptable performance. And although AI approaches may improve in performance, existing test suites have limited capability and examples of defects. So their approach was to develop a new software assurance data set and to benchmark state-of-the-art AI system and existing static analysis tools on their test suite, SA Bobby. So their SA Bobby was modeled after work done by Weston's group at Facebook, which developed a set of natural language processing tasks that were easy to automatically generate, yet difficult for AI systems to solve. So similarly, these researchers developed a code generator for detecting buffer overflow errors, and their generator intentionally develops very simple code, or very simple programs. It's valid C code. It develops valid C code programs that can have conditionals, loops, and unknown values such as those returned by the random function, rand. It complements existing software assurance data sets for training AI, and it's going to be included in NIST SARD. A code snippet from one of the generated programs is shown on the left with a conditional reasoning example. On the top line, there's a declaration of a character array that's 27 long, followed by a couple of assignments and a conditional, a check to see if entity 8 is greater than entity 1, which it actually is. 74 is greater than 45, so entity 8 is assigned to 64. And then we drop down to the last line, and is the last access safe? And why? I should ask why, because the answer is written here. Maybe I'll just explain. Okay, so no, it's not safe. Reason why is because the array was just declared to be 27 long, and there's an access to the 64th, to 64. So that question was, can deep learning learn from artificially generated test suites? And the results in summary were no, they can't do that yet. The chart at the left shows their test results. The y-axis is the F1 value, and the x-axis is the number of is the training set size in terms of number of files used for their deep learning AI system. The horizontal lines are the performance of static analysis tools that were used on the test, the training sets. The performance, starting from the least to greatest, was Clang did the worst, then CPP check, then from then a commercial tool which can't be named here. Now the deep learning the state-of-the-art deep learning AI system was run on the data, and the box plots shown show results from 10 runs on those that data set size. The results, as you see, going from 9,600, a training set size of 9,600 up to about 154,000, the performance approaches the highest performing static analysis tool as the training set size increases. However, although with a really large training set size, they found that the state-of-the-art AI system approached that static analysis tool performance. They also found that it failed to generalize. It wasn't learning, it was memorizing test results. So their future work planned includes better representations of the code to enable their system to learn from smaller test training set sizes, and adding integer computation to a neural net. There's a QR code if you want to scan that to get access to the draft of their paper about this work. So next I'll talk about some available technology to help organizations to scale testing. And this is available now for organizations that would like to use it. These technologies address all four enduring software challenges. One is secure coding standards. They're curated wisdom from thousands of contributors on the community wiki since 2006, and the standards can be used to develop analysis tools and train developers. The CERT C coding standard and C++ coding standard are available as free PDF downloads from 2016 and 2017. All of the latest guidelines in Java, C, C++, Perl, and Android are available on the CERT coding wiki as well. Recently, we've added precise mappings that I alluded to before when I was talking about my classifier research. The idea is that if you look at the Venn diagram on the bottom, if a condition of a program violates some CERT coding rule R and exhibits a CWE weakness W, then the kind of subcondition is in the overlap. And CWEs and CERT rules are conditions from different types of COFLA taxonomies. They have these various ways of overlapping. So in this precise mapping method, we define what kind of relationship, if overlapping how, and when they were mapped, and which versions, which is novel. Most mappings that you see online don't do that. So we work with MITRE last year and a bit this year to do that. So we've added the per rule CWE precise mappings to the CERT coding wiki. And we've added that metadata for the Juliet test suite that I talked about earlier. Our plan is to do this for each of the coding standards and for additional test suites. Scale, that static analysis alert auditing tool that I mentioned earlier in the classifier research, that is available. It's available on GitHub. And anybody that's interested in becoming a collaborator on my project, later, a version with enhanced features is also available. So we use Scale Insert as a research platform. We extend it with new features. Collaborators give us feedback and generate data required for our classifier research. And over the last 3 years, almost the entirety of new Scale features that have been added have been from the classifier research. So this is this screenshot shows an example of one of the new features that we've added recently. It's for creating a prioritization formula for prioritizing alerts using multiple factors. We've also added alert fusion for file path line condition, determinations history, automatically cascaded determinations from previous audits if you want to cascade them, classification schemes, and user field uploads. Another available technology is automated code repair to ensure memory safety. So this is not an automated, well, actually, although this is automated code repair, it also includes automated testing. So the goal of this work is taking a C code base and repairing potential bugs to enable a proof of memory safety. And the available technology is repair of integer overflows that lead to buffer overflows. This is part of Will Cleaver's automatic code repair research that he's going to talk about next. So So I open the floor to questions, or we can move on to the next. Okay, I'm hearing, we can take a couple questions. I could talk some more about Will's project.
So Laurie, I had one question. There are a number of projects that you mentioned that you were interested in collaborators. Can you maybe briefly describe what exactly kind of you're looking for, or maybe as what's the technical side of that, or what class of organization?
Okay, yes. I would love to have collaborators test out our entire architecture system that involves those 4 servers, and to have people, organizations audit code using the system and using the classifier. So that would be ideal. It would also be great to have organizations implement the API functions from their own static analysis alert auditing tools, and then use the other 3 servers we've developed to start using classifiers. I could really use feedback on how useful the API is, or enhancements that could be suggested. Separate from that, if you're just using your own static analysis tools, I would love to get alert auditing data, data that shows a static analysis alert, and what your auditors marked it as, true or false, and we can help you to sanitize your data, so you wouldn't send messages, or so you wouldn't provide data that talks about particular sensitive function names or programs or classes, but we would have enough data to help improve our classifiers. Yes? There's somebody.
So similar to my question earlier this morning, since DoD code is sometimes different from ordinary commercial code, is there any interesting challenges that you find in looking at DoD code as that commercial vendors would not usually encounter?
So I don't know. I feel like we don't have enough DoD code to know if there are differences in classifiers. I do know in terms of sensitivity, DoD code is very sensitive, and with our collaborators, we've worked with their security folks and our security folks to get the sanitizer approved for various organizations. But in terms of characterizing differences in the code or ways the classifiers would work, I don't know yet, but I would love more data to find out. Keep talking. Okay, no, I'm just plugging in.
Okay, thank you, Laurie.
All right.